by Zevalod Chulishev. This type is there for us all to see.
First of all, I'm grateful for the organizers to an opportunity to present the talk here. Thank you very much. The title is here, and I'm starting with a description of the problems. Then there will be two parts. So we study properties of time-dependent Schrödinger equation in which the special variable varies within a metric graph. So this is the equation. We study an asymptotical semiclassical solutions. So the effect of branching leads to occurrence of some non-trivial phenomena, and it is easier to trace them using the Gaussian packets. This means that the initial data for Cauchy problem for the non-stationary Schrödinger equation has such form, and it is localized in the neighborhood of 1 point. So we construct a corresponding semiclassical solution, and then in first part study the propagation of the solution on a arbitrary metric graph, and in the second solution on the study some statistical problems of this concerning with this solution. So the next subsection is some introductory facts about metric graph. It will be very quick because I'm sure that everybody here is quite familiar with this topic. So what is graph, and what kind of spaces could be established on the metric graph? And this is a definition of Schrödinger operator. So there are various type of transmission condition, but this is a transmission condition that is Neumann with some weights alpha. So this recondition is enough to define the Schrödinger operator, and sometimes I will use the Neumann transmission condition that are quite famous. So the first section, the next section is propagation of quantum Gaussian packet on a line. So I will recall this. It could be found in this book of Maslov. So there is exact formula for the moving Gaussian packet, and the solution depends on two Hamiltonian system. So two system of ordinary differential equation defines the Gaussian packet. And one of this system defines the velocity of packet, and the second one the shape of the packet. So the online it is clear, and then we are passing to the case of metric graphs. So this is the star graph with so the proposition is that if we have such graph and we are looking for the solution of this semiclassical non-stationary Schrödinger equation, then at any finite time the solution has the form of a finite, so it's the sum of Gaussian packets. It has a function of this given by this formula. So when initial Gaussian packet came to the vertex, it's divided into reflecting and 2 and -1 transmitted Gaussian packets, and the initial data for these new packets are the amplitudes of this packet are presented on this slide. So if the operator is self-adjoint, then the solution differs from the exact solution not more than O big of h to the power 1/2. So if we consider the Neumann transmission condition, then the amplitude would be divided in such a form. So these formulas for the star graph enable us to describe the propagation in case of arbitrary graph. So we obtain a solution of the non-stationary Schrödinger equation, and it has a form of the sum of Gaussian packets. And in the next section we will study the properties of these solutions. So this is the same formula, and we are study to how this n of t will changes in time. So some preliminary remarks. In this section, we consider only finite graphs with compact edges, and we can choose a Neumann transmission condition. When the Gaussian packets came to the vertex, it's divided. It gives birth to the exactly v vertex of degree v. It gives birth to exactly v new Gaussian packets. It's very interesting to study the non-big scattering case, but it isn't done yet. And we consider only clean graphs. This means graph without degrees of t. So this is analog of length. The quantity tj is the time in which the Gaussian packet passes the j's edge. It's defined by the Hamiltonian system, as it was in the first part. So and in my talk I will assume that these numbers are linearly independent over the rational numbers. So the next part is asymptotics for the number of Gaussian packets. The number of paths on graph is growing exponentially with time. So the question is what will happen to the number of packets n of t? And the answer is that it is growing polynomial. So if graph is compact and clean and the times are linearly independent over the rationals, this function could be written in such a way. And there is a lemma for the star graph. The following formula, it's not asymptotical, it's exact, holds for this star graph. So the number of packets could be expressed as the number of integral points that are lying on the side of k-dimensional simplex. So if we write down the leading asymptotic term, we obtain this formula for the star graph. So, but in general situation, one can also obtain the formula for the leading coefficient, but not all for all t, but for almost all t. So it follows from some number theoretical results. So the formula looks like this, and this is the total length of the graph. If in case of Laplace operator, so this is the formula for the leading term of the number of Gaussian packets as times goes to infinity. So this is some number theoretical references that I'm using, so maybe it's not important. So the next question is about the density of the Gaussian packets that are distributed on the graph. So the answer is that for almost all linearly independent over the q numbers of passing time, the number of Gaussian packets on the so this is a picture. We are consider the graph, and we are take some interval on an edge, and we are and we want to count the number of Gaussian packets on this interval. So the number of packets on the interval divided by the number of the packets on the whole graph is goes to this quantity. So this means that the Gaussian packets in this condition are distributed uniformly with time. But one can give an example of linearly independent Tj for which it is not so. So and there is still an open problem, description of the distribution of packets and calculation of this asymptotics in case of non-linearly independent overspeed, this Tj's. And the last section, it's some very small part. It's devoted to the propagation of energy on the infinite regular rooted tree. Such trees was investigated by many mathematicians, and Sobolev, Solomiak, Carlson, and many others. This is a definition of the energy on an edge. So this is about the tree, so it's regular. And for this binary tree, we start with one Gaussian packet that is here. In the root, we have Dirichlet boundary condition. And then we want to see what will happen to the energy. Will energy on edges goes to infinity because the volume of this graph is infinite. So it turns out that for binary tree, a quarter of this energy will stay on the first edge, and the half of the energy, it counts like a geometrical progression, will stay on the first edges. And in the case of arbitrary valence, this ratio, this portion will stay. So on this picture, this portion is staying. So this is the energy levels with energy with levels of the tree, and this is 1/4, and this, if we sum this up, it will be 1/2. So maybe that's all. Thank you for your attention.